like getting to the textbook or the homework website? Good. It's always a concern that there would be problems. So what I'm going to do, like I said, in class, is I'm going to give the lecture. Today's lab is dealing with this material, so it covers some of the bases for the lab as well, for the material that was listed in the syllabus for yesterday. So getting right into it, a very important question: what do physicists do? You know, what is our realm? We are looking at the physical universe. If you were to go through and read history of science, depending on whose history you read, you would see that back in the days of Aristotle, I'll show you the picture of him in a little bit, people studied physics and metaphysics, the physical world and the non-physical world. And so philosophy would be in that metaphysics area, and physics was all the physical world. But as knowledge increased, they started splitting things off. So we have biology that is studying the living things of the physical world. And then things got further refined, and we have chemistry that's studying the quantum physics interactions between atoms. As a physicist, we always believe that we're still the underlying study of everything. But of course, a chemist would say, hey, wait a minute. You know, we stand on our own. But we're studying the physical world, the things that we interact with. And so, you know, one of the things that I hope students will develop as they go through this class is wondering why things happen when they see them and being able to explain them. So an example is, you know, you see, I've had students say this, you know, well, one student sent me an email about how I ruined her life because she saw a car that was off the side of the road, an icy road. And instead of saying, that person, you know, slid off the road, like, oh, so the coefficient of friction was lower, and because of that didn't get enough, you know, and they started thinking about the physics of why the person slid off. But that, of course, is exactly what I want people to do. I want them to think about why things happen. So the goal is to understand the most basic laws that govern our universe. So these are pictures of things that all involve physics. Now you look at the birds migrating, and you might wonder where physics is in that. Who could give me an example where physics is in the birds migrating?
Formation reduces drag.
Okay, they actually fly in a formation that reduces drag, making it so that they can expend less energy for the entire flock to make the trip. Others? Well, there's a number of other things. One is just the basis of how does a bird fly, the aerodynamics that make it so it can develop the lift, which it took man a long time of studying flying animals before they figured out how it worked. There is the way they navigate, which is, yes, Cassie?
And their bones are hollow, so they're lighter as well.
Yeah, gives them an advantage over me in terms of being able to fly. There's also my belly, but that's beside the point. They also use the Earth's magnetic fields for navigation. There are some things like bees that use the polarization of light for navigation. They can actually, they're using light, but they can navigate in a cloudy day because they're using the polarization rather than the direct light. You have the little iPhone there. How's the iPhone using physics? Better question, is there anything it does that doesn't? And the answer is no. Anybody got some examples?
Just picking your position and calculating the speed and projecting the time.
Okay. It has a GPS radio that is communicating with multiple satellites and using the time delay between the time indicated by each satellite and what the time actually is when your radio receives it to determine how far away it is from each, triangulates position. That in and of itself is pretty complicated. Then it uses the changing in that with time to figure out how fast you're going. Of course, the underlying principle that all of our little electronics run on is transistors, which is a Nobel Prize physics discovery. You have the screen technologies, which vary from one to another. You have the touch. All of that is very complicated physics stuff. I was hoping no one would say, if I fall it, if I let go, it falls and hits the ground. That would also be true, but that's not what you want to do with your smartphone. The microwave, I'll just go in this. Very interesting discovery about a microwave, as I understand the story. A researcher who was working with microwaves in a research facility put his lunch on top of a little microwave generator, and then when he went to eat his lunch, he had a melted chocolate bar, and he's like, what the heck? And so did some studying and discovered that the microwaves had caused the chocolate bar to melt, and from that we have developed our microwave ovens, which, by the way, do not damage your food. My stepdaughter threw out the microwave when she moved into her great-grandmother's house because it damages food. That's just not true. There's no science to that at all. But anyway, moving on. This next picture down is a nice little cross-section of somebody's head. We're not interested in the head so much as the physics that goes into being able to send waves through your melon and receive those waves and interpret those waves so that we can see what's going on in there. And then we have some membrane here that has way more things than I understand because I don't understand biology. But the way all of these things work comes down to physics. And so some people study biophysics and they study that as part of their physics. So just something to illustrate the broad range of physics there in those pictures. One of the things that can be a downer in any class is the words we use, the jargon. And in physics, we have a lot of specialized meanings. So we use terms like work all the time, right? I'm working right now. You can tell because I'm sweating. Okay. In physics, we have a very specific definition for work. So a lot of words, we'll have to make sure I already know them, surprisingly enough, but you understand what we mean by specific jargon words as they come up in a physics sense. And of course, I will try to describe those so that you can differentiate between your everyday usage and the usage in physics. And here are a couple words that I used in this morning's lecture just to get us started. Speed. I think everybody knows what speed is, right? You're driving your car, you've got a speedometer, and it tells you how fast you're traveling. Speed is the distance you cover divided by the time it takes to cover it. And it will be topic du jour mañana. That was 3 languages in that sentence. Velocity is speed with direction. And oftentimes people will use those two words interchangeably. And most times we don't even think about the fact that they're meaning something different. The sad fact is I, your very own physics teacher, fall into that same trap. I will say velocity when I mean speed and speed when I mean velocity, not intentionally, but because in my brain they get jumbled together. I know the difference, but when I'm speaking, they'll just one or the other will come out. But we need to know that they're not actually synonyms, that velocity has direction involved, but speed does not have direction. So your speedometer tells you speed, it does not tell you velocity. If you have a compass in your speedometer, together you can get the velocity. Mass and weight. This is one that some physicists say, let's not worry about it. We'll just confuse people. I'm not one of them. I am very, very careful in the difference between mass and weight. Weight is a force, something that pushes. Weight is the result of gravitational force acting on your body or some body. Mass is an inherent property of matter. I have mass, you have mass, we all have mass. A small amount of that mass comes from the inherent mass of the quarks that make up the atoms, and a much bigger part comes from the interactions with Well, the Higgs boson's believed. And I say it's believed because I don't understand it yet. My textbook last year, I was teaching a class of particle physics, described it kind of like if you were to take a spoon and move it around, you can measure the mass of the spoon by how much force you have to push on it to make it move. But then if you put it in honey, you would get a completely different measurement because of honey resisting the motion. And then it said, and likewise, the quarks have really tiny masses, but in them going through the Higgs bosons, that's acting like the honey, making it so they appear to have much bigger mass. Okay, that's not something you're ever going to get tested on. But knowing that mass is an inherent quantity of matter, whereas weight is a force, two completely different things. If you go from here to the moon, your mass isn't going to change unless you eat food or exhaust food. But your weight will change considerably because you have a different acceleration of gravity on the moon compared to here. So they don't just scale together. They do scale together if you stay the same place on Earth. If you go from here to Denver, you'll lose a little weight. Really small amount. But the acceleration of gravity is smaller in Denver, so you lose a little. Go up to Pikes Peak, you lose a little more. Okay, so just a couple more jargon things. Size of physics. Physics deals with sizes from the minute to the extraordinarily large. So this here, how many people have seen this picture right here? Okay, we've got a few. So, Tori, what is it?
I believe that's something, I don't totally know, but I believe that's an image of the scanning tunnel electron microscope or something.
Well, scan tunnel microscope.
Yes, scanning tunnel microscope. I don't remember if that one was atoms or not. I've seen a lot of similar pictures, like the little dog.
This is the first. This is the first. That's why I put it. This one was done when I was in graduate school. They used, I think it was the scanning tunneling microscope. First, they used the tip to move atoms, to place atoms where you see each one of those blue dots. And then they used the STM to go over and take an image. And so they placed atoms, and then they're looking and showing the atoms. That's pretty impressive because you think, atoms are really tiny. The size of a nucleus is on the order of 10 to the minus 15th meters. The size of the atom itself is a little bit bigger because you have the electron cloud. But they're manipulating and being able to observe things that small. And then we have an intermediate picture here. You probably recognize this is the Earth. And see, that's like the Arabian Peninsula, right? So we know where we are. And then this is the moon, a picture of the Earth taken from the moon. And here we're seeing, looking out, and I don't know where that is, but we have an emission nebula, and the purple part's emission nebula. The blue part is reflection nebula. But we're seeing things that are many light years away. A light year is the distance light travels in 1 year. Extremely far away. So the sizes in physics range from really minute to really large. And the fact is, if you were to become a physicist, you would specialize in a certain area, and your world wouldn't be huge like that. It would be just this little area. Numbers. One of the things that we're going to be looking at today is we're going to take some measurements and record them, record the uncertainties in those measurements, and try to analyze the uncertainties. But numbers by themselves are useless. If I were simply to tell you that I have an object and it's 189 long, would that help you very much? You would not know necessarily if you could fit that in your lunchbox, you could fit it in the room. But if I said it's 189 centimeters long, then we have units and we can look and say, okay, well, here's 100 centimeters, so 189 is just a little under 2 of these. It turns out to be my height. So when you have those units, it starts to make sense. And so virtually everything you measure is going to have units. There are things that don't, like counting numbers, 1, 2, 3, 4, 5. Those don't have units. On the other hand, if you're talking about your age, you have units, 1, 2, 3, 4, 5 years versus 1, 2, 3, 4, 5 decades. Thankfully, I'm not to that upper number yet. So units are really important. Anytime in lab, when you make a measurement or you record a number, like from a calculation, you need to have the units with it. If you just have the naked number without units, you'll lose points. Because numbers without units basically don't mean anything to us. Yeah, this last example is good. The term paper is due in 3 seconds, minutes, days, months, years. I'd go with decades on that to be safe. Standard for time. The standard for time, that is the standard unit that we use in physics, is the second. Not the only unit. We use lots of units that relate to the second, but the second is the standard. And the origin of the second is, I don't know. I really don't know. I feel like I should. But we have, since 1967, well, I did a lot more work on this than I have up here. Since 1967, the definition of the second has been 9,192,631,770 cycles of a certain hyperfine emission from krypton, cesium. And in 1997, they added, okay, this is only if the krypton is at rest at 0 Kelvin, which is actually redundant because if it's 0 Kelvin, it's going to be virtually at rest. And we can get very close to 0 Kelvin, but not actually to 0 Kelvin. But we have a very distinct definition now of what a second is. This number, this really big, annoying number, comes from matching up what had been used previously as a second to something that they figured was very reproducible anywhere in the world. And so this picture, it kind of looks like some kind of rocket or something. What that is looking down from the top on an atomic clock that uses the cascade of these, well, to measure time. It's big. So we have a very good standard for time, something that can be reproduced anywhere in the world, anywhere in the universe. That's a goal in physics, to have a standard that is not wishy-washy. Now let's compare that to the standard of, I think next is the mass. Nope, the distance. Old measurements of mass. The foot. How long is a foot?
12 inches.
Okay, 12 inches. It actually depends on where you are. There are things like, the length of a ruler's foot. You guys have heard Napoleon was super short, right?
He's 5'6".
It depends, well, in the units used in France when he was emperor, whatever he was, I don't remember the title. I think it was 5'2", but they used a different unit for what a foot and an inch was then. And so if we were to measure him by today's standards, he was like 5'6", like you said, which still sounds somewhat diminutive, but for his time, he was above average height. So he actually shouldn't be considered a short man because compared to his contemporaries, he was a little bit taller than average. Having a measurement that doesn't change with time is kind of important. So the meter is the standard we use in physics. We use the metric system, or I looked up so I could pronounce it right, but I'm certainly going to do it wrong. Système International d'Unités. International System for Units. And the meter is the standard for distance. So we have in the classroom meter sticks. They're nominally 1 meter long. I say nominally because the ends, this one doesn't have caps and the ends are wearing down, so it's probably a little bit shorter than a meter. The ones that have end caps are longer than a meter. So these are nominally 1 meter sticks. We break that down to centimeters, decimeters. Okay, we never use decimeters. Centimeters, millimeters, and so on. Kilometers for large distances. If you wanted to pronounce it correctly, you'd say kilometer. I actually went 1 full school year back when I was like my 3rd year teaching saying kilometers, but I felt like such an idiot saying kilometers every time that I just reverted back to saying kilometers. When the meter was originally defined, they said, well, let's choose something that's reproducible. And their reproducible was 1/10 millionth of the distance from the North Pole to the equator along the prime meridian. Really reproducible, right? All you've got to do is measure that distance and divide by 10 million. Well, and their meter wasn't really that close because their surveying wasn't so accurate. In 1983, the meter was redefined to be the distance that light travels in 299,792,458 seconds exactly. So the meter is based on the speed of light. Now, the fact is, we take the speed of light, said exactly, we take that number to be exactly the speed of light. If you do a measurement that somehow shows the speed of light is different, what you've actually done is change the length of a meter. Now, this does have to be the speed of light in vacuum because the speed of light is different when it goes through like glass than it is in vacuum. But we now have a standard that, now it's, there's another definition here. It must be from my astronomy class that I did all of the extra work and put in the extra slides. Yes?
Okay, maybe I'm making this too complicated, but so if there's like a solar eclipse, did that already happen then in the past? Because the light takes so long to get here?
8 minutes.
8 minutes.
Yeah, it takes 8 minutes for light to get to here from the sun. So if there's a solar eclipse, you're going to see it, well, actually, the solar eclipse is the moon passing between us and the sun. That's actually much closer, but the light left the sun 8 minutes before it came to us.
Okay.
Right.
So not that.
Yeah, not that different. But if you look at the nearest star is Proxima Centauri. And Proxima Centauri, named Proxima Centauri because it's proximal to us, tricky scientists, is about 4.1 light years away. So if we were to see Proxima Centauri do something, we would actually be watching over 4 years after it happened. We call that in astronomy the look-back time. So the distance in light years is the look-back time in years. Then we get to mass. The kilogram is the standard unit for mass, and a kilogram is defined as the mass of this piece of platinum iridium. This piece, no other piece. So if you wanted to test your mass, we have I have here a mass that's 500 grams, half a kilogram. If I wanted to test this, I would have to take it to Paris at the institute that houses that and get permission to compare the mass. That's not convenient at all. And scientists are working on trying to find a more convenient standard, one that can be reproduced in labs so everybody can have a standard for mass. Now, this ingot here has twins that have been made, but this is the official one. And I read an article a year or two ago that said, shockingly, it appears that it's changing mass. This ingot, it's made of platinum iridium because it is very inert. It's not going to interact with anything. But then to be safe, they have it in a double vacuum chamber. If you look here, you see the outer bell jar, but inside there's another bell jar. And so they pump out both of those to keep it so that you don't have any air in there, so that there's nothing it could interact with. So you have something that's very inert and nothing for it to interact with. And it still appears to be changing mass, which has people shaking their heads. So that's our standard. The unit is the kilogram. So I've talked about 3 units. The units for, oh my goodness, I guess I won't use the clicker questions because I never did start up. Actually, I can do it still. I only have 2 clicker questions for the day. The units I've talked about are the units for time, distance, and speed. And you are going to be very comfortable with those sometime soon. So unit for time, second. Unit for mass, kilogram. Unit for length, meter. And unit for my brain, non-existent. I started up a web browser instead of starting up what I wanted to.
What channel is it again?
It's channel 33. It says it probably somewhere behind the screen. Okay, now here is a table showing all of the basic units. This is every 1, 2, 3, 4, 5, 6, 7. Yep. Every single one of the fundamental units we have. Now, if you look at that, you see it's just 7, and you're like, that doesn't seem right. It seems like there ought to be more. The first 3 are the only ones, well, no, excuse me, we're going to use this one too. The first 3 in kelvins are the only ones we're going to use this semester. Next semester we'll use the electric current, the mole. We won't use the candela. So we're only going to use 6 of those 7. Those are the basic units. Everything else is a derived unit, is made up of those. So for instance, speed. Speed, I said, was the distance something travels divided by the time it takes. So the units for speed are, I'll put a number here, in meters per second. It's a derived unit. It's based on 2 of the fundamental units. This one. So here is the most common example we're going to be using, the Newton. A kilogram times a meter per second squared is a Newton. We will generally just write N, but Newton equals kilogram times meter per second squared. So the Newton is not fundamental, it's derived based on 3 of our fundamental units. And like everything that we're going to study for the next month at least is just going to be those 3 units mixed in different ways. Just some arcane concepts here. When you use the symbol for Newton or something like that based on a person's name, it's a capital for the symbol. So newtons are capital N. Amps, short for ampere, is a capital A. When we write out the name of the unit, like it's 5 newtons, we write it with the lowercase n. So we don't get it confused with the dude. You know, it's not 5 Isaac Newtons, it's 5 units of newtons. Now, does that matter? It just matters for comprehension when you're reading the book. You remember, oh, if that's lowercase, it's clearly just talking about the units. But when you write the abbreviation, you write it with the capital. I have this section in here. It comes from a previous textbook, but it can be confusing to me. When we talk about something increases by a factor of 2, well, that's pretty simple. You know, the value in my stock increased by a factor of 2, never. I wish it would. Instead, it's been decreasing dramatically. That's pretty simple. Increased by a factor of 2 means you multiply it by 2. But what if I said the value of my stock decreased by a factor of 2? When you say decreased by a factor of 2, it means you divide by that number. So decreased by a factor of 2 would mean that my stock dropped in half, which it seems it has in the last, we're inheriting some stock, and the value has gone down a lot since the day that my wife's grandmother died. So understanding what something means when it says increased by a factor of 2 or decreased by a factor of 2 is kind of important. Another thing we like to talk about percents. If something increases by 5%, then it's 1 plus 5% more. So 1 plus 5/100ths more. In other words, if something increases by 5%, it's that much times the original. Which is simple. Now, if something decreases by 5%, you would have the same thing. It'd be 1 minus the 0.05, so 0.95%. And this is where I have the first clicker question. I think it's this slide. I'm going to bring this one up. Yep. Suppose the Adventist Book Center has, I believe the sign says ABC Book Center. So the Adventist Book Center has Bibles that normally cost $20, but they're on a 50% off sale. And you have a coupon to take 50% off of any sale price. What's the price for a Bible with this sale and coupon combined? Not including tax, that's right. We did this transaction in Montana. No, it'll just take the last one. Okay, because I haven't updated or given you a chance on my class to update your clickers to begin with, I will assume that these 13, 14, 15, 16 people are the only ones with the clickers. So the answers that we got were 0, 0, 1, 2, 1, 1. Oh, how I wish this was correct. But it's not. I've seen all kinds of silly things like this. When I was teaching at PUC, we went from making 150% of a number to making 155% of that number. And our financial vice president, who knew nothing about finance, said, "You got a 5% raise." Oh, how I wish he was right, but that's not the way math works. If you go from 150 to 155, your change was 5 over the starting number 150. So that's going to be, see, 150 is genius. I should be able to do this in my sleep. That would be 30. So 1/30th, so that's equal to 3.3% increase, not a 5% increase. Now, in this case here, you have a 50% off, so you start with your original price, and then you have a 50% off, which means 1 minus 0.5, and then you have another 50% off, so another 1 minus 0.5. Of course, 1 minus 0.5 is a stupid way of writing 0.5. So this is the original times 0.5 times 0.5. 0.5 times 0.5 is 0.25, 1/4. I could have put 1/2 times 1/2, and we'd all see it's 1/4. And so you have 50% off. 50% off means that you have to pay just 1/4 of the full value, or the answer that 13 people got, $5. True story. When I was a kid, my mom was one of the people who would stack coupons. They'd have like double coupon and a sale. And sometimes the coupon was like 30 cents off and the sale was 50 cents per. And so mom would double it. And we got paid like $1 per flat of soda that we would take away from the store. It's kind of cool. My siblings and I wanted to take all of it, but mom was like, no. I figure they're paying us to take it. Why shouldn't we? Okay, some of the important names in physics. We have Aristotle. Aristotle was a very important philosopher, and he had a lot of principles that stood for a long time in physics. One of those principles had to do with why things move. He believed that everything was made up of one of 4 elements. Everything on Earth was made up of one of 4 elements. Those elements were Earth, which has a natural position. Earth goes down. Then you have water that has a natural position. It lays on top of the earth. Right? Your lakes are sitting on top of the earth. The streams on top of the earth. And then you had air. Natural position was on top of the water. And then you had fire. You see that smoke rises, and so the natural position for the fire must be up above the air. And so we have this stratification of the natural positions of everything. And so then we take something like this ball, and he says, why does the ball fall when I let go? Well, it must fall because it has earth in it, and the natural position for earth is on the earth, so it goes down. But then you say, well, if I take this ball and I drop it, and I take this piece of paper and I drop it, are they going to fall at the same rate? No. Which one's going to fall faster? Okay, so we have experience to tell us the ball. Well, in physics, we always do experiments, and we see, yep, it sure does. And so Aristotle says, well, the ball must have more earth in it than the paper, and thus it wants to be on the ground more. I'm not going to bend over. Because it wants to be on the ground more, it falls faster. He also believed that it fell at a constant rate, depending on how much it had of each of those things. Yeah, I'm old. If I bend over, I might not bend up again. That's a problem. Thanks. I'll try not to do something silly like drop them on the floor again. So Aristotle came up with a lot of ideas and principles, most of which have now been overturned as people learn more. But you have to have a starting point. So other great people, Galileo Galilei. I love saying both of his names. It just sounds cool to me. Why is Galileo so special? Well, he really believed that you should study by doing experiments. Aristotle thought that if it sounded beautiful, it must be true. And Galileo said, no, let's do some experiments. So you've all heard of the experiment that was probably never done, of Galileo going to the top of the Leaning Tower of Pisa and dropping, well, having his assistant drop 2 balls of different sizes. Now, this was a test to see if Aristotle was right, because Aristotle had said that if you have a ball that has more earth in it, hence making it heavier, it will fall at a constant rate but faster than one with less earth. So if you take 2 balls and let's say one weighs 5 pounds and one weighs 10 pounds, and I drop them, according to Aristotle, the 10-pound ball is going to fall twice as fast. It'll take half as long to get to the ground. And so Galileo believed that no, you actually didn't have this earth thing making it fall, that it was something completely different. And so he had a different theory, did the test, and the test clearly showed, I mean, you can all imagine, if you drop a 5-pound ball and a 10-pound ball off of a very tall building, how much difference are you going to have in the times for them to hit the ground? Very small. It's not going to take twice as long for the small one as it does for the big one. So that would conclusively disprove Aristotle. Now, I said he probably never did it. Historians believe that it was a story that he used as an example for people to draw just that conclusion, to see that Aristotle wasn't right. If he had been Einstein, we would have called it a Gedanken experiment, an experiment in the head. What he did do was he did lots of experiments on inclined planes, on ramps, to determine his outcomes. And of course, he did not invent the telescope, but he was the first person to use the telescope to systematically study the skies. And we have a lot of advances from him. And he wrote a book where he mocked the Pope. And because he wrote a book where he mocked the Pope, who happened to be a close personal friend of his, he was forced to recant and say that the earth didn't move. It's very interesting. Isaac Newton, a very interesting character with nice long flowing locks. Isaac Newton, I just have to tell you, he didn't have a great childhood. When he was a kid, his dad died. But his mom remarried. But his mom's new hubby said, hey, I only married the woman. That can't be mine. And so he was actually raised by his grandmother. And when he went to school, he was bored with school. And he did things like create little inventions to impress the ladies. And so people who were his sponsors, people who were raising him said, well, clearly this guy is not cut out for school because he's like a D student. He just doesn't do what the teachers want. He doesn't pay attention. School is not his thing. So they got him a job as a shepherd. And as a shepherd, he sat there and made his little inventions while the sheep wandered off. So he was a failed shepherd and a failed student. And people said, well, okay, the kid's clearly brilliant. We've got to figure out a way to get through to him. Got sponsorship, went to the university. Was still kind of, just goofing around until his last year when he realized, if I don't straighten up and fly right, they're going to make me get a job again. And getting a job stinks. So he actually did well his senior year. He was hired as a house scientist for one of the professors, which essentially is like being a postdoc, graduate student or something like that. He taught some classes, and then the best thing that could have ever happened to Isaac Newton happened. The Black Plague. Because when the Black Plague came, and I know I mentioned this morning, when the Black Plague came, you have a communicable disease. Well, we don't want all of the young, bright minds of our generation to die off. And so we send them all back home and cancel school for a year and a half. And so what is somebody whose job is teaching physics going to do when school is canceled for a year and a half? I have a really good idea. I'm going to Huntington Beach. That's my happy place. But yeah, Newton went back to Grandma's house and said, I can study physics non-stop. And so he did pretty much all of his amazing work in that year and a half. In that year and a half, he developed his 3 laws of motion. They're going to be very important to you in the coming months. He developed his universal law of gravitation. He developed calculus. He did a bunch of optics work. He was a busy beaver. And then he came back and he really didn't write much. It took him about 20 years to write about his research in that very short amount of time. And he did other important things in his life, like he was I don't know what they call him in Great Britain, but he served in the House of, House of Commons or the House of Lords, one of them 2 houses. And he is on record as speaking once. And so everybody was really excited when he first stood up to speak. And what he said was, "It's a bit drafty in here. Can we close that window?" So he probably wasn't much of a politician. But he was an amazing physicist and a top religious scholar. He spent a lot of time studying religion. He wrote a set of Bible concordances, and apparently Ellen White and him had very similar interpretations of the Bible. I've never read either of them, honestly. I tried to read one of them. I tried to read Ellen White's, but I got attention span this long. I can go a half page, maybe. Okay, Marie Curie. She's partially here because she's a woman. She's a very important woman. There are actually other women that are probably more important than her, such as Maria Geppert-Meyer, the person who came up with the shell model for the nucleus of an atom. But she and her husband, Pierre, were leading researchers with nuclear physics. He died when he fell down in front of a cart and it ran over his head and crushed his skull. She died of I believe it was a cancer secondary to her radiation exposure from research. But they did some amazing research. If you look back on that periodic table, there's polonium, which is named after Poland because of Marie Curie. There's also curium, clearly named after the Curie family. They had 2 daughters, one of which also won a Nobel Prize. So they have 1 daughter. How'd you like to be that one daughter out of everyone in the family who didn't win a Nobel Prize? Mom won a Nobel Prize, Dad won a Nobel Prize, sister won a Nobel Prize. But she's another great physicist who helped us to understand what's going on in nuclear physics. Niels Bohr, famous for the Bohr model. And we will study Curie and Bohr in the 2nd semester, so I'm going to not bore you with Bohr. Okay. Important things in science. What makes science? Now, you guys have probably all taken more than one science class in the past, so this is probably not new to you. But some terminology, the difference in a model, in a theory, and a law. A model is an analogy. It's something to help you understand how something else works. So an example we use in astronomy is the celestial sphere. Now, back in the day of Aristotle believed that all of the stars in the sky were on one big crystal sphere. So he believed it was real. We don't believe that to be real at all. We believe all the stars are just out there on their own. But we still talk about the celestial sphere as a way of locating where stars are because it helps us to identify where they are because they don't move very much with respect to each other because they're so far away. And so we can treat them as if they're on this big celestial sphere even though we know they are not. So it's a model. It's not a correct model, but it's one that's very beneficial, very helpful for us in identifying positions for the stars. A theory is what you get when a hypothesis has been tested a few times. A theory is an explanation for patterns in nature that have been supported by testing. So you don't have a theory just like, well, I've come up with a theory on this. When you say, I've come up with it's a hypothesis, which means kind of like an educated guess. After you've tested it, then it can become a theory. Then we have laws. Laws are concise language to describe general patterns and can often be described by simple equations such as this one here, Newton's second law of motion. Laws are kind of like an elevated theory that is general and simple. So there's not a huge difference between laws and theories. It's kind of just like laws are special theories. Models are completely different. And the scientific method is the basis of all science. The scientific method, I forgot about that. Here's a model of an atom. We know that electrons aren't doing loops around nuclei, right? but it's still a model that helps us think about the atom correctly. So when you do scientific work, first you do need to read up on what others have done, learn from others' experience and the tests they've made, and then to test other people's ideas, not accept them as fact. And that's the same thing you should be doing in all of your classes, not just physics. You need to test what the teacher says, not just take it as fact. Teacher said that this was the greatest president ever. Well, what's the evidence? You need to think about it yourself and not just take it from the teacher. Invent an explanation or hypothesis to explain something, test the hypothesis, report it to others so that they can test it, and if your hypothesis withstands all the criticisms and tests, then it can become a theory. Now, this is my personal version of the scientific method. It starts with observing something interesting, because you really don't do science if you're not curious about why something happens. So you observe something interesting, and then you say, now why did that happen? And you come with the hypothesis, an educated guess, that needs to be, number one, based on scientific ideas. Oops, number one is explain the observation, but I still want to say this one. Based on scientific ideas. You don't have a hypothesis that's based on, well, no linkage. Example I used in my class yesterday was, different class obviously, was the sun rises in the east because Washington, D.C. is in the east. There's no scientific linkage between those two. It's not based on scientific ideas. So that would not be a scientific hypothesis. It also needs to explain the observation. I haven't figured out why Washington, D.C. being in the east would explain why the sun rises in the east. And it needs to be something that makes predictions that you can test. And then the next step is you devise a test of a prediction. And if it passes the test, you have not proven the hypothesis. You've confirmed in this situation its prediction was correct, but you have lots of other situations that need to be tested. And by lots, I mean an infinite number. And so if it passes the test, you just go back and you retest a different prediction. If it fails the test, you have just proven your hypothesis wrong. You can never prove something right in science, but you can prove something wrong. And if you prove it wrong, you now have new information, and you come back and you develop a better hypothesis because now you know what it's not. It's like that old joke about carving a piece of marble. Well, how do you carve this marble into this beautiful, David or whatever? Well, I just chip away everything that's not David, and what's left? That's basically what science is doing. We are taking the facts we have and trying to put together a picture of how it works. Then we test it, and if we find that we're wrong, well, we've taken away that part, make another hypothesis, keep testing, you narrow it down. So science should, by its method, eventually reach truth. How long does it take to reach truth? Forever. But it should get there eventually. Whew. You guys aren't hot, right? I'm the only one here sweating? Yeah. I hate that. All right. This is our last clicker question. At what point is the scientific method completed? My lines are off here. I was like, oh boy, I missed. All right. Well, I'm going to assume everybody's answered at this point because we've had plenty of time to get the clickers out. Well, no, that would have been a bad assumption. Now I'll assume. So we have 00017. The scientific process is never done. That's correct. You never have something proven right. You're never done. If you go to graduate school and you do research, your research will also never be done. It'll just keep progressing down the road. You learn more and you learn more and you learn more. Okay, now I think this is going to bring us to talking about today's lab, which will be short. Accuracy versus precision. When you make measurements, you can be accurate or you can be precise. Let's just take the simple example here. I'm going to throw the ball to Chad. Okay, somebody over here's got to catch the ball. Okay, so threw that one to Chad. Oh boy. I got to throw it back. No. Okay. So now I throw it to Chad again. All right, there we go. Now my two throws They weren't very accurate. They didn't come close to Chad. But they were precise because they both came to Jaron, right? Jaron. Well, no, hey, there's a football player, Jaron Langley. So, accuracy is a measurement of how close you're coming to the target. Precision is how reproducible you are. And sometimes you can make measurements that are perfectly reproducible, but you made the same mistake every time and you were largely inaccurate. Sometimes you have measurements that are all over the place, but they're clustered around something. They're reasonably accurate, but not very precise. So I've got a picture here that makes it better. Oh, with this here, it's very clear. Is this one precise or accurate? Both or neither? Oh, you can't. Okay, let me get... You really can just barely see it. Okay, I have this. I'll make a pointer. I can do this. Maybe. It should change to a pointer. Nope. Did earlier. Okay, here's the pointer. Is this precise or accurate? Okay, what about this one? Okay, so this one is fairly accurate. Not perfect. This one's very precise, but not very accurate. So this diagram here shows you a kind of continuum between those. I know it's pretty simple, but hey, we don't have that much hard stuff to start physics. Over here you have low precision and low accuracy. It used trueness on the head, graph, but they're not very tightly clustered and they're not clustered around the bullseye. If you go upward in this, you're becoming more accurate. They're coming more to clustering around the bullseye. If you go to the right, they're becoming more precise, clustering closer together. And so up here is what you want, something that is both precise and accurate. Now you might wonder, why are we talking about that? Because when we make experiments, such as we are in lab today, you're going to be, you'll want to know, am I reproducible? You can't really test your accuracy unless you know what it's supposed to be, but you can test to see if you're reproducible, if you are precise. So anytime you make measurements, you're going to make multiple measurements. Today I only require you to make 3 measurements of each thing. 3 is like the minimum number so you can see if there's some kind of clustering or not. So the reason we do multiple trials of the same measurement is so we can see if it's reproducible. I bet you that's got this on it. Nope, not yet. Okay, this is an example with a graduate cylinder. You're measuring the volume. Over here you see we have the meniscus. It's concave downward because water has a lower energy when it's touching glass than when it's touching itself. And so it actually climbs up the walls because it's going to a lower energy state. If you had mercury, it goes the other way because mercury has lower energy if it's touching itself than if it's touching glass. You guys know that? Okay, so we have this, and we want to measure the volume in the graduate cylinder. You've all learned, I hope, that when you measure from the bottom of the meniscus. So there is a dashed line there where the bottom of the meniscus is. Now, if you just read this meniscus, it's marked across here. What value would you read? Okay, I heard 31.6 milliliters. Now, how did you come up with 31.6? Okay. You see it's between 31 and 32. And then you have to guess the last one. And that's what we do when we're using something like that. We read what we can. So we read that it's between 31 and 32. And then we estimate how far it is between the last two. And so Tori estimated that it was 6/10 of the way across. Somebody else might have read this and said, I think that's 8/10. And who am I to say if it's 6/10 or 8/10? Right? That's a personal judgment. But what we can say is there's an uncertainty in that measurement. There's an uncertainty based on how well you can predict. So then the next step in this process is identifying how much could you have been off. So, Tori, since this was your number, how much do you think you could have conceivably been off in your measurement over here? Just choose a number. It's you.
Half a milliliter, I don't know.
Okay, so she said half a milliliter. So what she's saying is it could go anywhere from the separation there, anywhere between those two. Well, the top one's probably a little high. I forget I'm super zoomed in, so could be anywhere between there. Now that was a fairly generous, amount of error that she allowed herself. I would have said that she's probably good to around, plus or minus 0.2. You have to make your judgment for yourself. I'm not here to tell you what the correct judgment is. It's a judgment call. And so Tori would have said plus or minus 0.5 milliliters. This here is the uncertainty. And where did that uncertainty come from? It was your judgment on how well you could estimate. Now, in your experiment today, you're going to be doing some uncertainties. And it's not like there is a correct uncertainty, but there are incorrect uncertainties. You're going to be asked, how long does it take for a ball to drop 1 meter? And, if you say an hour, you're going to lose credit because that's not a reasonable prediction. And if you say my uncertainty is around an hour, you'll lose credit because that's not a reasonable uncertainty. Right? But within the realm of reasonable, anything goes. It's your judgment. Now here we only looked at how well we could read this. But there might be some other issues that affect our uncertainty. What else would affect our uncertainty in the total volume for this measurement?
It's like on its own thing or something.
Okay, if it's not perfectly vertical, over here.
I was going to say circus.
Okay. Right?
Precision and your instrumentation. That's how it works.
Okay, if it's a sloppily made, I just bought these, and I was looking at this, taking a picture and blowing it up with my iPhone. I'm not sure that these are really precisely marked. And so that can come into play. It could be that your instrument is not super precise. Yeah.
If you were measuring different liquids at different temperatures, that would...
Okay, there's another thing that could change. The temperature would change. There's also the fact that we're not counting this volume right here. Right? Just because we measured the bottom of the meniscus doesn't mean that there was no liquid above the meniscus. And so that's also going to be an error. So when you look at your error, your plus or minus 0.5 starts sounding better when you realize, wait, there's these other things. And so when you're looking at uncertainty in a measurement, you need to consider all of the sources that you can think of that would cause uncertainty and how much total uncertainty you have. Usually the largest uncertainty is going to be the one that you use to set your uncertainty because it's usually, this one's this big, this one's this big. Well, what's this compared to that? But that's one of the goals today is to understand that uncertainty. Okay, so here are pictures I took of measuring. We're going to measure with just 2 devices. We're only going to do parts 1 and 2 of today's lab, not 3 and 4. Why? Because I did the lecture here beforehand. So here I've shown measuring with a ruler. Funny story. I ordered 4 or 5 packs of rulers. I got 4 single rulers. I called them and said, hey, I would have never paid this price for a single ruler. Oh, yeah, it was mismarked. But they gave them to me, so now we have 4 new rulers. These new rulers have nice rounded edges. I like that because people always want to use the end of a ruler in a measurement, but the end of the ruler is not calibrated. Right? If you use the end of this meter stick, even though this is all broken up, you can still see the line that's supposed to be 0, which means 0 is not out here at the end. 0 is where that line is. So you shouldn't use the ends. Those new rulers, you couldn't use the end. That's why it has that rounded plastic over the end, so you won't be tempted to make a mistake there. And so we look at this and you measure. And so for a rough guess from what you can see right now, let me dim the lights to make it a little clearer. How long would you say, or how wide in this case, this piece of card was? Okay, somewhere around 9.5 centimeters. Now, let's zoom in and see if we can do this better. Uh-oh. Yeah, I went in between. Now, we have to look at both ends. This end here, I tried to match it up as good as I could, but you know what? Actually, within the color registration, that might still be correct. Let's assume that I have that one lined up right. We don't have to worry about it, that it's close. Look at the other end here, zoom in, and I can see, wow, that's just barely past 9.4. And so I would say, let's write bigger than that. It's between 9.4 and 9.5, and at most I would say 9.41. It'd be either 9.40 or 9.41, and then I need my uncertainty, plus or minus, and that would be, in this case where I have it nice and zoomed in, I can be pretty sure I'm clearly within 0.02. Then my units, centimeters. There's a complete measurement. I have measured out to 1 decimal place farther than is shown on the instrument, and then I've estimated my uncertainty, and they are in the same digit. If your uncertainty was like 0.1 and this went out to 0.41, why'd you write the 1? You didn't know it, right? You just said that your uncertainty was bigger than that. So make those match up. So that's how we make a measurement like that. Now this one here, obviously I'm not measuring the same thing, so we're not going to get the same number. But this here is a vernier caliper. Looks like this, except for, I think, your table. Everybody has a nice new one. I have yours. First thing to note with these is, see these little gaps here? Don't measure in those gaps. It's all the way closed. If that was the correct measuring place, there would be no gap. Those are just so that it doesn't bind up when you close it all the way. Now these have a little screw. Loosen it up to move it. You tighten it up so it will hold a number and not slide on you. So loosen it up and then you can just move it. It has a little wheel here for you to move it with your thumb. And if I want to measure something like, let's say, the diameter of this knurled nut, put it on here, tighten it down, take it out, and then I'm ready to measure. Now I have a prepared one here that we can measure with. We call this funny measuring thing, the thing that's got the oval on it, a vernier. Named after some dude. Now, before I get too carried away, this lower one says cm at the end, this upper one says in. One's in centimeters, one's in inches. If you get one of the old ones, some of the old ones say mm. And that mm stands for metric measure, not for millimeters. Just there to confuse you. So if I look at this, that's as zoomed in as, wow, that doesn't look as good as it does. Actually, yeah, maybe it'll look better if I do this. Nope, no, that doesn't look any better. There's a little pull-up artifact in here. That didn't change it. I'm trying to change it. Come on. Okay, it's a little better because it doesn't have the pull-up artifact. The first thing you do when you make this measurement is you look where this indicator here falls. So if you look, where does that fall? Between what and what? Between blank and blank. I haven't heard an actual... Okay, it is between 3 and 4, but we have smaller markings. Okay, so it's between 3.1 and 3.2, so I start with 3.1 because I know it's between those two. Then, instead of estimating the next digit, we can read the next digit precisely. We can look here and we say, which line on this side, can you see that mark going up and down? Yeah. Which line on this side matches up best with the line on this side? This here is the 0 marker. 1, 2, 3, 4. This one here is 5. I've zoomed in so much it looks horrible. Trust me, that was a 5 and a 0. And so on. So you look at these, and which one do you think lines up the best? Okay? So I had an answer 5, this one right here. And so that is the last digit. Now notice that was 5 on this side, not on this side. It doesn't matter which one you line up with on this side, it's which one it is on this side. So I have then 3.15, and then my uncertainty is going to be plus or minus, how many lines could I have been off in my estimate of which one lines up best? Right, we chose that this one here lined up best. How far off could I have reasonably been in that assessment? Just one line. So it's just plus or minus 0.01 centimeters. So by using that vernier, see, I was blowing up way too much. By using that vernier, we're able to get a more precise measurement. We can measure with greater detail. So the vernier caliper is better for measuring than the meter stick. There are also some other things. You're going to be measuring a ball. If I wanted to measure the diameter of the ball on the meter stick, I have to worry about what direction is my head when I sight. Because if I don't have my head directly over, then I will have a parallax issue. That's actually why you have mirrors on analog gauges. So when you read it so your eye sees the marker and then the reflection of the marker on top of it. If you see the reflection separate, that means your eye's not in the right place and you move. Do you guys know that? You guys probably, half of you at least probably haven't even seen an analog thing with the little reflector behind it. If I want to measure with this, I put it in the calipers and I should be able to get a pretty accurate measurement. Now with this ball, depending on the angle I put it in, I might get a different measurement. You're going to be measuring the diameter ball, so make sure when you make measurements, you take the ball out, flip it around, put it back in to make the next measurement. So you're measuring a different aspect in the ball to try to make sure if the ball is uniform, what your real uncertainty is in that regard. Other uses for these, this here will measure an inner diameter, has the knife edges facing out. This measures an outer diameter, has the edges facing in. This here is for measuring depth. So if I want to know how deep is, this, I can go like that until it touches, and then I can read off of my vernier caliper how long that was sticking out. So that's the tools we're going to use for measuring today. We are so close to getting started. We just have to learn about propagating error. That is, we make a measurement. Any measurement you make, not only does it have to have units, it needs to have an uncertainty to indicate how precise you believe that measurement is. If you tell me, I think that you are 6 feet tall plus or minus a foot, well, sure, yeah, that works. Not very useful. But if you say, I think you're 6'2" plus or minus a quarter inch, well, that's a much more useful measurement of my height. So you have the uncertainty there so somebody knows how useful that information is. When you're doing something like adding numbers or multiplying numbers, how you track the uncertainty can be difficult. These equations are in your lab guide, 2 different places. And they tell you if you have something that's like the result is equal to a constant multiplied by your variable x, then your uncertainty in the result is just your constant a times the uncertainty in the variable x. Pretty simple. If you're adding numbers, you just add the uncertainties. So if I have two people's heights and each one has an uncertainty, one's standing on the head of the other, then my uncertainty in the total height would just be the sum of the uncertainty in the first person, that's uncertainty in the second person. When you're doing multiplication and division, it starts getting more complicated. You calculate what percent was your error. So delta x over x is the percent uncertainty in x. And if we want to find the uncertainty and the resultant with things that are multiplied or divided, we add up the percentages. And so if I have x times y divided by z, it doesn't matter that it's divided by z and multiplying for x and y. It's still a percentage error in x plus percentage error in y plus percentage error in z is my total percentage error. And then the final one, the final one is kind of silly because it's just a special case of the one above it. Right? If I have x raised to the third power, that's just x times x times x, and I could have just done this. But if it was to the 2.5, this would be more helpful. So that's how we deal with them technically. In your lab, you're not going to do this. This lab is the only one that has instructions to do it, but it's in part 4, and I said we're not, or part 3, and I said we're not doing part 3. So you're not going to actually use these equations, but it's important to see that we do have a systematic way of dealing with error. The true way of doing it involves a little calculus, but this is the way we show it for non-calculus. Instead of doing that, we're going to keep track of significant figures. And a lot of people have seen significant figures, and what I've determined is a lot of people don't know significant figures even though they think they do. So I have to go over it to make sure you know what they are. So the first rule here, all digits, including zeros, are significant unless they are placeholders. What's a placeholder? It's a zero that is only there to move the digits to the right position. So if I look at this first example, 101, this 0 is not a placeholder, it's a significant digit. Any 0 that's between two significant digits, by definition, is always significant. So this one, how many total significant figures does it have? 3. This one here, 100.0. This 0 here has no reason to be there, does it? So the fact that it's there means it must not be a placeholder, it must be significant. And since that's significant and this is significant, all of them are significant, and it has 4. What about this one? It's only 1 because these two zeros are placeholders. Those are necessary to get the 1 out to the right place. Now, when you add or subtract numbers, and this is the rule most people don't know. Most people know how to deal with significant figures when you multiply or divide, but not when you add or subtract. When you add or subtract numbers, the greatest of the least significant digits of all the numbers becomes the least significant digit of the answer. To me, that sounds mealy-mouthed when I say it. I think it's a lot better just to show an example. So here is the example I'm going to do. If I want to do this right, the easiest thing for me to do is to write my addition vertically. Three, two, 1, 0. Okay, so there I've shown my addition. Now I had this thing, the least significant digit. Least significant digit means I'm looking at the significant digits in each number and which one is the rightmost for each number. So I can look at this and say, okay, this one here was the least significant digit for that number. This one here for that number. What about this final one? What's its least significant digit? You actually don't know. It's ambiguous. It could be the 1 or it could be the 0. You don't know. In textbook problems, assume the maximum number it could have been, just to be safe. So we will assume here that this one here is again significant. So I look at those and I say, what's the greatest of the 3 numbers that's not 1, 2, 3, 4, 5, but in terms of units, tens, hundreds? What's the greatest of those 3 that I pointed to? It's the units. Right? 2 of them were in the units and 1 was in the tenths. So the greatest of the least significant digits is that column. And so that means my number is significant to there. So I'd usually, instead of drawing that circle, I usually just draw a dashed line, and everything to the left of the dashed line is significant. And so the correct answer for this would be 3, 3, 3, 4. Why don't I include that 0.2? Because that 0.2 is insignificant. It's not actually meaningful. This 123 could have been 123.3 for all I know, which would have significantly changed that 0.2. So I don't show it. Now, an important rule with significant figures: never, ever apply significant figures until you get to your final answer. You don't want to throw away information during the calculation. But when you get your final answer, then apply your significant figures. Also, I should point out, significant figures are not perfect. The equations I showed you in the previous page are pretty close to perfect, but you could have something like it's either 1.0 or 1.01 or 0.99. You have 3 significant digits in 1.01 and 2 in 0.99, but the difference in the two is just 0.02. So that illustrates a flaw with using significant digits. It's not a perfect way of tracking your uncertainty, but it's a lot easier than using the previous equations. Okay, the third rule when multiplying or dividing numbers, the lowest number of significant digits is the number of significant digits in your answer. So if I took those same 3 numbers and I multiplied them, you look at your answer and you say, how many significant digits do I have in that 473,676 number? And your answer is 2, because 1.2 only had 2 significant digits. So when I added those numbers, I had 4 significant digits. When I multiplied them, I only had 2 significant digits. And I said, a lot of students I found know this rule right off the bat, but this rule here they didn't know. So that's why I spent the time on it. Any questions about the significant figures?
So you want that in addition to error, or the uncertainty thing?
You actually determine your significant digits from your uncertainty. The digit where you have uncertainty is your last significant digit. And so instead of keeping the uncertainty, we're just going to use significant digits after that. So in calculations, you won't be using plus or minuses. You'll just be using significant digits after that. That's actually an important thing. All measurements need a plus or minus value in units. Calculations just need the units and the correct significant figures. Okay, if you notice, we are down to the third to last page. Lab reports. Today will be your first lab report. It's going to be a short lab. It better be because we only have an hour and 10 minutes left in lab. Your lab report is going to be turned in as an uploaded PDF document on Moodle. Now that is why I gave you that little handout on how to scan papers using the printers around campus. We have 2 different photocopiers in our division, and the instructions are slightly different from one to the other. So I didn't go through and check this to see if there were any changes for one versus the other, because they're probably different for a lot of them, but once you get the idea, you can do it. So you have here some instructions on how to scan. You can either scan and email to yourself, or you can scan and save to a USB drive that you stick into the photocopier. I also strongly recommend that you do something like get this free tool, PDFill PDF Tools, which I put it in the same folder that has the lectures, so you can just go on Moodle, the one that has lectures, and just download it from there to make it simple for you to find. That allows you to do things like rotate pages if you scan them and they're upside down or something. It allows you to separate, reorder pages, to take multiple PDF documents and combine them into one. So that allows you to take, things like you made a PDF document from the computer in lab and you have the PDF scans of your write-up, and you can combine them together in one document. And it's actually very simple, which is a benefit. Now, if you have a Mac, you can actually do these things with the preview app in the Mac. It takes a little more work than it does using this. The things that you have, if you look in your lab guide, pages Roman numeral 2 through 4, we have the stuff for the lab report. And your lab report should start with the title. So today's title is measurements. You should have that at the top. And then you need your name, and also put your partner's name. Make sure you say, this is me and this is my partner. Well, you don't say, this is me. But you would say, Jared Nelson is Nelson, right? And Hannah Chung. And put partner next to Hannah Chung so we know it's Hannah is the partner, not you. And the date on which you did it. Then we have the purpose. And the purpose is why you're doing the lab. You can quote the purpose for all I care. You can paraphrase or you can quote it. Each lab, actually I think I forgot one, but each lab is supposed to have at the top a purpose. So for instance, next week's lab's purpose is to discover the relationship between position time and velocity time graphs. You can just quote the purpose. Then we get to the hypothesis. The hypothesis is worth 5 points, and the hypothesis is going to be something to help us develop a feeling for how the scientific method works. So a hypothesis is an educated guess about why something occurs. So you have to start with an observation. Now, today's experiment, you're going to be dropping a ball 1 meter, and then for your test of your hypothesis, I've specified what your test is going to be. You're going to be dropping the ball 2 meters. And your hypothesis needs to be something that will predict how long it takes for the ball to drop 2 meters. So your hypothesis will be something about the ball dropping that would make a prediction of how long it will take to drop 2 meters. And the hypothesis at this point, what do you know about balls dropping? Well, only what you knew before taking physics classes. We haven't learned any real physics yet, right? So I'm not asking for anything that's super complicated here. Just something that explains why the ball takes this amount of time to fall, and then that can be used to extrapolate, to predict what would happen if you doubled the distance. So you need to have your hypothesis written out. Now, the partners, you'll be working in groups of 2, except for there'll be one group of 3, I think, because we have an odd number. The partners will work together on coming up with their hypothesis. You won't have separate hypotheses for each partner. And then you're going to do the test together and your analysis together. So you need to have the observation, which in this case is going to be, I observe a ball falling 1 meter. And then your hypothesis, I believe it falls and, takes this time to fall because of this. And then you're going to have for your test, I'm going to drop it 2 meters, and according to my hypothesis, it should take twice as long, it should take more than twice as long, or less than twice as long. That's all as precise as I care to be. It'll take, only 1.5 times as long, whatever you can predict from your hypothesis. It doesn't have to be an exact time. And then when you do the actual test, you will have a result and you'll say, my hypothesis was proven incorrect, or, and why, or my hypothesis was confirmed because it matched. So that's what this hypothesis and test part are. So you need to write out at the beginning of your lab what your hypothesis is and how you're going to test it and what the outcome you expect will be, what outcome would prove you wrong. You see that test part is 15 points compared to the 5 for the hypothesis because you have that explanation. Then you have your equations. For this lab, we don't have any equations, so we can skip over that. The apparatus you're using. For this lab, your apparatus are going to be a meter stick, micrometer, and then you can just put computer for timing. Oh, not micrometer. I cut out the micrometer. This here is the vernier caliper. And then your procedure. Your procedure should, number 1, not be copying everything that it says in the lab guide. Your procedure should explain what you're doing in an abbreviated fashion, so it should be much shorter than the lab guide, but in a clear enough form that somebody else could repeat it. Right? So you don't have to have all the long verbiage in there, but it needs to be enough that somebody else could repeat the experiment from reading your lab report. Then we have data calculations and discussion. Oh, wait. data calculations discussion. That's where you're going to put your data. That's where you're going to do your calculations and discuss things like, okay, so I'm going to do this. Oh, that went wrong. If something goes wrong, you should make sure you have a notation there of what went wrong, why it went wrong, how you corrected it. In this, anytime you take data, make sure you put data in tables. So, for instance, you're going to have trial and time. Make sure for the time you have the units and the uncertainty. So I'm going to put plus or minus seconds because the units for time are going to be seconds. You need to determine what your uncertainty is for your timing. That's part of the experiment, so I'm clearly not going to put a number there. If you put your number up here in the top of the table, it is assumed that all numbers underneath it have that uncertainty, so you don't need to rewrite it for each number in the table if you have it in the title. If you don't put it in the title, then you need to put it with each number. Then I have trials 1, 2, and 3 for me, and I'll also have trials 1, 2, and 3 for my partner. And then you put your values, put your partner's values. The reason we're putting a table like that is for two good reasons. Number one is for the grader, which right now is me because I don't have TA yet, to make so the grader can find the data and scan it quickly. Number two is for you, so you can scan it quickly, look to see if there is a trend or not. So if you don't put it in tables, you'll lose some points there because organization is an important thing. If you take a measurement and you think it's wrong, don't erase it. In science, you should never erase. It's a rule. That's why you're supposed to use pens in science, like I said at the beginning, because if you use pencil, people are tempted to erase. If you think a number is wrong, so let's say I had 1.275 and I said, ooh, that was wrong, put a single line through it. That indicates you think it was wrong, but it's still readable, so somebody can come back and read it, because it might be that it turned out you were incorrect in identifying it as wrong. After you do all your discussion and whatever, you'll have your results. Your result is a very brief, concise statement about what you found. In this lab, I specified exactly what your results will be. If you look on page 5, in bold, I said, in this activity results are the time it took for the ball to fall 1 meter and 2 meters, the diameter of the ball, and then you can skip the last 3 parts because we're not doing those. So those are your results. Those are all things that already appeared in your calculations. Your results are not new things. They are just the highlights that you had from your data and calculations and discussion. Then the final part is the conclusions. The conclusions are your statement about if you confirmed your hypothesis or disproved it, if the lab succeeded in what it set out to do, if you learned the things you're supposed to learn, what things went swimmingly, what things went poorly and could have been improved. Those are the kinds of things that go in the conclusions. So conclusions is on the lines of what I learned, about physics, whereas results are the important results I got in the experiment. The results will all have previously appeared above. Conclusions, not so much. Any questions about the write-up? Okay, simple poll. When is the write-up going to be due? I didn't say that yet. Where is the write-up going to be turned in? On Moodle. So on Moodle, you'll find the measurements under laboratory. You click on there, it'll have a place for you to upload your PDF file. And use something like PDF fill tool to combine into one. Now, when is it due? By Thursday at 11:55 p.m. So you're supposed to have everything finished when you leave, but you have to have time to go scan things and whatnot. And so I give you another couple days just so people can get it all scanned and turned in on time, without having time pressures. Okay, today specifically, you have instructions that I think are very clear because I wrote them. First, you're going to estimate the time it takes to drop a ball 1 meter. That does not mean drop the ball, time it, and write that down as your estimate. And I want you to write an estimate before you move on. I want everybody to think about now how long do I think it's going to take, and write down that number. That number, like I said, if it's an hour, it's going to lose points. But if it's reasonable, if it's something that looks like you thought about and tried to come up with a good number, that'll be fine. You're putting down what you think. Then you're going to just draw the ball a meter a few times, not timing per se, but just observing, and have a chance to revise. Say, I think that I was pretty good, or, ooh, I think I over or underestimated time and it should have been this. What have you done there? You've observed something without measuring. You're giving yourself a chance to revise, make a more educated guess. You're also then going to estimate how much error you think you could have in that, what your uncertainty is in that estimate for the time. Then you're actually going to drop the ball. To drop the ball, you're going to use just a simple timer on the laptops. There are 2 power strips in that thing for charging the laptops, and apparently one of them got turned off. So some of the laptops don't have much charge. If they fail, well, we'll find a way. So if you go to the laptop and you click on the link for Physics 151, there, it will bring up this folder that right now just has General Physics Lab spreadsheet, which you're going to use, and the timer. Double click the timer, it opens up. See this down here? I'll put it up here at the top of the screen. I start it by pressing like the space bar. I stop it by pressing the space bar. If I press the space bar a 3rd time, it both resets and starts. So I don't need to ever go through a reset cycle. I just do that and it starts again. And so that's what you're using for measuring your timing. And record your data in your note, well, in whatever you're going to turn in. Then you're going to take your data and go to the spreadsheet. So here's the spreadsheet. Open that up. And under the Statistics tab, you have this and you put in your data. Only have to do, I think it says 3 trials. So you put in your time. And it calculates the average and the standard deviation for you. Only keep out in standard deviation the same number of digits as you have for your average. And by same number, I mean the least significant digits should be the same. So don't put this whole long number. That's stupid. If it's, the average is out to the hundredths, so I would just put, my standard deviation is 2.10. And then you're going to compare your average to your prediction and your standard deviation to your predicted uncertainty. And you have some questions to answer along the way. You need to make sure you read through. I tried to make the questions very clear. They all start with Q/C. So hey, this is something I better make sure I answer. And if you put Q/C 1, 2, 3 when you answer, it'll make it a lot easier for me to identify, yes, you answered that right here. And you can answer the questions just as you're going along through the data discussion and calculation section. So you drop the ball, you measure the times, and you calculate those statistics and answer your questions. Then I did not write it here because I wasn't thinking. Now you're going to drop the ball from a 2-meter height. I have a 2-meter stick in the next room. We'll bring out the 2-meter stick. Drop the ball from 2 meters, measure the time for that to fall, and that's how you're going to test your hypothesis. The part 2 is measuring the diameter of the ball. You're going to take your ball and measure the diameter 3 times with the meter stick and 3 times with the vernier calipers. For all of these things, both you and all of them except for the 2-meter drop. For the 1-meter drops and for the diameters, everybody needs to make their own measurements, and you should have in your report your measurements and your partner's measurements. For the dropping at 2 meters, you can just do 1 set of measurements for the 2 of you. And after you've done that, skip parts 3 and 4 so you're done. Any questions?
So we record both measurements for both partners, but only when we drop it, we only do just 1 partner.
Yeah, so
Okay.
I mean, if you're looking at how much data do you have in your report, you have your 3 measurements for dropping 1 meter, your partner's 3 measurements for dropping 1 meter, your combined 3 measurements for dropping 2 meters, your 6 measurements for diameter, 3 with the meter stick and 3 with the vernier calipers, and your partner's 6 measurements. That's the entire group today.
Okay. Oh, sorry.
That is question. Okay, now for location, obviously there's not room here. We have another lab room identical to this on the other side of that room. I will open up another door, but you can go through to that room. And we want groups of 2. There will be 1 group of 3 because it's an odd number. Okay, go ahead and begin. Oh, you will need a ball. 1 ball per group, not 1 ball per person. They're here. Since I'm walking back to the back, I'll just start handing them out. Well, no, I won't because you need to have your group first. Yeah. Yes. So get your group of 2 and actually I'll put them back here so they forgot you don't have groups. I can't get it to you. Your vernier caliper and that kind of stuff is in the drawer at the end of your table.